Okay, so let's solve some equations and inequalities using algebraic functions. So we're going to start out kind of easy. This is just a polynomial. It's just a degree 2. The highest power degree, the highest power of x is 2, so that's why I say it's degree 2. And we did one like this the other day, and you've done like ones like this many times before. This is a factorization problem. Of course, you can use the quadratic formula, but I prefer to try to factor it first. And this is where you try to think of the two numbers that multiply out to 24 and add up to negative 10. I'm thinking 6 and 4, and it would have to be a negative 6 and a negative 4, because those would add up to negative 10, and they would still multiply out to positive 24. So x minus 6, x minus 4, and as we know, that means, and I'm going to jump to the answer, but let me just talk this out. That means one of these factors must be 0 if it's set equal to 0. And so if this one is 0, then that's going to tell me x equals 6. If this one is 0, that's going to tell me x equals 4. And yeah, so let me say a word. So far I've been careful about putting these logical arrows, like every time I write an equation and then another equation, either I put an arrow going this way, or maybe I put a bidirectional arrow like the if and only if one. And of course, people aren't used to doing that. People are used to just writing equation after equation after equation. And the truth is that can be okay as long as you are thinking about it. If I were to put the arrows, and maybe I will now that I'm talking about it, they would all be bidirectional arrows. From this step to this step is just factorization. In fact, this and this are the exact same thing. So that would be if and only if. And as we went over, when you have an equation that says a product of two things is 0, that's true if and only if one of the two factors is 0, and that's how we got that. So we are confident that we got all solutions. And like I was saying, it's not strictly necessary to always write these arrows. I encourage you to do it, or at least think about it. But as long as you're thinking about it, you can just write equation after equation like this and be confident that you really did find all solutions. But it is going to come up. It is going to matter in these examples. So let's do another one, say this one. So I want to get x by itself. X is right here. So the first thing I want to do is get rid of the 1. So this is 2 square root of x equals 8. And then I want to divide by 2. So I'll write square root of x equals 4. And then what do I do to get x by itself? I square both sides. And the square root of x squared is just x. And before I go any farther, let me see, where was this stuff from last time? Here we go. What am I doing? Ah, there we go. Right, so I had just gone from here to here, and I told you the square root of x squared is just x. And you might be saying, you just told me in the last video that it wasn't. But here's what I actually said. if you have, and I'm just pointing out to these notes here about the absolute value, if you have the square on the inside of the square root, that's when you need to write absolute value. If you have, like this one, the square is on the outside of the square root, then it's just x. So once again, let me draw the arrows. I did something similar to the last example where I just wrote equation after equation after equation. There's no logical connection written in between the equations. So let me go in and put in the arrows. So from this step to this step, all I did is I added a number to both sides. That goes both directions. From this step to this step, all I did is I divided by 2, or you could say I multiplied by a half. And since I multiplied both sides by a number that isn't 0, that's both directions. Then I squared both sides. When I square both sides, I am applying a function to both sides. And since I'm applying a function to both sides, I'm allowed to apply any function I want to both sides and write an arrow going to the right. If that function is 1-to-1, then I also get an arrow going to the left, like a bidirectional arrow. So the question is, do I have to only write one direction, or am I allowed to write two directions? And that's a question of whether this function that I applied is a 1-to-1 function. The function that I applied to both sides is the function that squares both sides. So I would say I did f of both sides, where f is the function x squared. And is that a 1-to-1 function? No, it's not. This function, just like all even powers of x, this is not a 1-to-1 function. So we really don't get the left arrow here. And so we have a slight issue. Of course, this last step is just simplifying, so that would be bidirectional. But we have a disconnect. We took a step that wasn't a bidirectional step. And I'm really kind of belaboring this, but and I have hardly any space to do this, but what do you do when this happens? You just check your answer. That's all you do. When the instructions say find all solutions, the fact that all of the arrows go forward, and they do all go forward, almost all of them go in both directions, but even this one goes forward. So since I had forward arrows the whole way through, I'm confident that any solutions there are were found. I'm not confident that all of the things that I found are solutions. So that's why you check them. You go back to the original equation and you just check it. 2 times the square root of 16 minus 1 would be 2 times 4, right? Square root of 16 is 4. 2 times 4 minus 1, which is indeed 7. And that's what it's supposed to be. So as it turns out, the number that I found really was a solution, but there was a reason why we checked it. Now, if this seems silly to you, let me do another example to show you why we check these things. So this time I wrote almost the same equation, except I replaced a 7 with a -7. And let me run through this the same way. I would add 1 to both sides. I would multiply both sides by a half. I would square both sides. And I would get that, right? And the arrows would be very similar, right? Because all I did here is I added a number to both sides. All I did here is I multiplied both sides by a half, which is not 0. And then all I did, well, what I did here is I squared both sides, and when we squared both sides, that was when the arrow only went forward. And so we should check our answer again. But when I check it, I get 2 times 3 minus 1. That would be 6 minus 1, which is 5. It's not -7. So what did I know? Well, roughly speaking, I knew the same thing I knew last time, which is that any solutions that there are were among the numbers that I found. What I'm not confident of is that all of the things that I found really are solutions. Any solutions there are in the world are on this list of things that I found. It turns out I only found one. But if there's any solution, it has to be this. But that doesn't mean that this is a solution. That's why we check it. As it turned out that this was not a solution, so what that means is that there is no solution. This was the only chance for this equation to have a solution, and it didn't work out. So, and that's okay. Sometimes when you're solving an equation, when it says find all solutions, sometimes the answer is that there are none. And that's why we check. And that's why we care about these arrows, because the arrows tell us when we have to check and when we don't. And again, once you get good at this, once you feel natural about it, you don't really have to write all of the arrows. You'll just kind of get when you're solving an equation and you know you have to check your answer, you'll just kind of get a feeling, and you'll know that you're supposed to check your answer. Of course, it never hurts to check your answer anyway, just in case you made a mistake. But there are some situations where you have to check your answer, even if you didn't make a mistake. Like there's nothing wrong with the work that we did here when we got x equals 9. And we carefully took care of the arrows just so we would know that we don't just stop here and declare that x equals 9 is the solution. We were careful, so we knew that we had to check our answer. But it's not that we made a mistake to get this. It's just that sometimes you get a number that doesn't turn out to be a solution, even though you didn't make a mistake. And that's why we look at the arrows. Yeah, good. All right, so I should warn you, D gets ugly. So here I've got the square root of something plus the square root of something else equals 4. So here's what I'm going to do. Roughly speaking, the way you get rid of square roots is by squaring both sides. So that's what I'm going to do. I'm going to square both sides. And since what I'm doing is I'm squaring both sides, just like last time, that is only a forward arrow. And now let me simplify this. Actually, this is a bit painstaking, but what does it mean to square this? It means multiply it by itself. And this is just simplifying, so this is bidirectional. Of course, we already have a break in the bidirectionality of this. We already have an arrow that only goes one direction, but I'll still worry about these. And I'm multiplying this out. So I do this one times this one, and a square root times itself, that just cancels. When I'm taking a square root and I'm squaring it, so that just turns into 3x minus 2. And then I'm foiling, right? So I did the first time the first. Now let me do the outer. So it's this times this. Like that. And then I'm going to do the inner. But actually, the inner is the same thing as the outer, right? It's the same two numbers that you're multiplying together. So instead of writing that again, let me just put a 2 here, because that would just double up what we already had. And then, like I said, I'm doing FOIL, so now I'm on the L, which is the last. So I'm doing this times this, and then that's a square root times itself, so I just get x plus 2 equals 16. And again, this step is just simplifying. Okay, let me simplify this just a bit more. So I've got a 3x and an x. That makes a 4x. I've got a negative 2 and a positive 2, so that just goes away. So I've got this. Now I'm going to do a couple of things at once. I'm going to move, well, actually, let me talk about the big picture here. So we started with something that had square roots in it, and we said we don't like that. Let's square both sides, so that'll make the square roots go away. And in some places, that did make the square roots go away. Like when we were multiplying this out, and I had a square root times itself, that's a spot where a square root went away. But then if you look at the end result, it still has square roots in it. So it's not like all the square roots are gone. We are in a better position, though. We did make some progress, but the square roots just aren't gone. So what are we going to do? Well, I'm going to square both sides again, but I'm not going to do it immediately. I'm going to kind of isolate the part with the square root in it. That way, when I square both sides, everything's clean and the square root just goes away. Meaning, so once again, I'm going to isolate the part with the square root in it. So I'm going to subtract the 4x, and then I'm going to divide by 2. And this is a tough problem. And I don't want to show a painstaking amount of work. So let me do those two things at once. I'm subtracting 4x, and I'm dividing by 2. Those are both things that I can do with a bidirectional arrow. And what would the result be? After taking the 4x over, I'd have 16 minus 4x, and then I would divide everything by 2, and I would get 8 minus 2x. So that's just the result of subtracting the 4x and then dividing everything by 2. Okay. Then we square both sides, and this is an arrow that only goes forward. Actually, well, okay, so here's what I'll do. I'm squaring both sides, and what that does is it takes this square root off and it takes this square root off. There's still the multiplication, though, of course. So this side is now just this times this, but there's no square roots. This side is this. Okay, what's next? I multiply this out, so I get a 3x squared. Okay, so this times this would be a 6x, and then this times this would be a minus 2x, so I would have a plus 4x, and then negative 2 times positive 2 would be negative 4. All right, now I square this side out. I'm going to use the formula where when you're squaring something like this, I get the first thing squared, and then I'm going to have 2 times the first thing times the second thing, and then I'm going to have the second thing squared. So once again, first thing squared. And now I'm going to have 2 times the first thing times the second thing. And then I'm going to have the second thing squared. All right. Picking up here, this would be... I'm going to move everything, let's say I'm going to move everything to the right. I'm going to subtract everything that's on the left over to the right. So now the left is just going to be 0, and the right is going to be what? Okay, let me do this in an organized way. Let's take care of the x squared terms first. So I've got a 4x squared, and I'm subtracting a 3x squared, so that's just x squared. Where are my x's? I've got this one. This would be negative 32x, and then I'm subtracting 4x, so negative 36x. And then I would have this 64, and I would move this over so it's a plus 4, so plus 68. Okay, so where are we now? Well, the good news is we have no more square roots. That's great news. And in fact, what we have now is basically, it's a lot like, where did it go? It's a lot like the first one we did. Yeah, it's a lot like this one. This is just a factorization problem. This is thinking of 2 numbers, and these are kind of big, but if you try to think of 2 numbers that multiply out to 68 and add up to 36, you will think of negative 2 and negative 34. So I get x equals 2 or x equals 34. Am I done? No. Why? Because I had some arrows that were not bidirectional. In fact, I had this one and I had this one. So once again, I found a list of numbers. Since all of the arrows went forward, I'm confident that any solutions are on this list. Now, there's a few possibilities here. These could both be genuine solutions, or one of them could be a solution and the other could not, or neither could be a solution. That's also possible. We just have to check. For x equals 2, I get the square root of this looks like the square root of 6 minus 2. That's the square root of 4, which is 2. And then this is also the square root of 4, which is 2. And sure enough, that equals 4, which is what it's supposed to be. Let's check the other one. X equals 34. Oh, is this going to be ugly? No, maybe not that bad. Well, the numbers are big, but 3 times 34 is 102. Yeah, it's 102. And so then I subtract 2 and I get 100, and the square root of that is 10. That wasn't so painful. Here I've got the square root of 36, which is 6. And that doesn't equal 4. It's supposed to equal 4, but it doesn't. So x equals 34 is not a solution. So when I want to list all solutions, I just say x equals 2. So yeah, sorry that one was a bit painful, but it's important to really illustrate why you have to check your answers in some cases. And again, like I said last time, it's not that we did anything wrong when we got x equals 34. It's not that we did anything wrong. It's just that when we got to this point, we weren't done because a necessary step of the problem is to check your answers. And that's necessary for this problem because the arrows aren't bidirectional the whole way. Of course, once again, it never hurts to check your answers, but sometimes when you check your answers, you're really just seeing whether you made a mistake. Other times when you're checking your answers, it's because you really, really have to, even if you're sure you didn't make a mistake. It's a necessary step of the problem to check your answers. And you really can come up with numbers that will not be solutions. That's why you have to check them. All right. Now let's do a couple of easy ones that are just about solving inequalities and absolute values. So if you have an inequality like this, it's the absolute value of something and it's set less than or equal to a number. Here's the rule. That's true if and only if, and here's what I'm going to do. This is going to be an inequality with like 3 things, and the thing in the middle is an x. The thing on the right is just going to be a 3. The thing on the left is going to be a negative 3. That's what you do. You put this thing in the middle, you put this thing on the right, and negative of this is on the left. And this, so the instructions are find all solutions. I would be okay if you just leave this as your solution. Of course, it's also possible to put this in interval notation. Interval notation would be bracket -3 to 3. This is including -3 and 3. That's indicated by the brackets, and that's because of this is less than or equal to. By the way, if this was just less than, without the equal to, if this was just less than, then this one and this one would be less than, and I would use parentheses here. That would be the only difference. In fact, let's take a look at the next example, and let me make that a less than, just so you see an example that has a less than there. So let's solve this one. This one's basically as easy. I put this thing in the middle. These are both going to be less thans because this is less than. And then 5, -5. Now I have a little bit more work to do. When you're working with an inequality like this, you're allowed to do, let me put in the arrow, but you're allowed to do any operation you would normally be allowed to do to an inequality as long as you do it to all 3 things. So if I want to get x by itself, I would like to subtract 1, and I'm going to do that to all 3 things. And that's a step that I can do that's if and only if. So I'm subtracting 1 from everything, so this would now be a -6. This one would now be a 4. And then I'm going to divide everything by 2. That's like multiplying by half. So -3 less than x less than 2. I can also indicate that in interval notation by writing -3 to 2 with parentheses. The parentheses indicate that these numbers aren't included, and I know that because these are strictly less than instead of being less than or equal to. All right, so I'll leave you with that for today.